Hi everyone, in this video I will continue discussion on the physical properties and ND material and I have discussed the absorbing boundary conditions, then SDA software, concrete 3D and damage 3D and the remaining parameters are to be discussed now. In order to continue this discussion, I have this isotropic image definition here, and let's just make it more easy. If you are using with the two-plane isotropic limit model, then this is the best way to consider here. And for elastic isotropic material, I mean those material that are uh, uh, isotropic and have same deformation in all three directions. For example, if you have a material, right, and you are trying to check its performance, and this is the material parameter sample, and you are trying to check its performance after compression, right? And after compression, that material behaves like this in this direction, right, in 3D. And similarly, same deformation is observed in this direction, right? Similarly on this direction and on this direction as well. So this is for the isotropic damage in two plane, right? And 2 point, sorry. And for example, the density, if we consider 2300 as a random density, and you consider the elasticity to be this much with Poisson ratio this much. In tension threshold, you can control this parameter at hardening softening law behavior. One mean it's completely hardening, zero mean it's not hardening, with the BT parameter set to 1. Similarly for compression, and we have this beta parameter. This is biaxial compression parameter. So let's just test it, and you can see you can check its performance based on various codes, and you will observe here uh, the data that you are getting here is this much response here with all these trains here. Since it is in uniaxial direction, so and it is isotropic material, elastic isotropic material. So we are not seeing any kind of deformation in it, and it's only considered as elastic parameter here. However, with these other control parameters in tension and compression, it can be controlled here. So just like that, the orthotropic material is different, and for orthotropic material, we need the Young modulus in x direction and Young modulus in y direction with z direction, and similarly, we need the shear modulus between x and y and z and x direction, and Poisson ratio for xy plane, for yz plane, and for zx plane, and after that, we need ratio between the isotropic strength and the orthotropic strength. So if this ratio is larger, it will impact the results very drastically in the analysis. So anyways, let's look at here and just test it. So you can then map these results. For example, if I consider it 0.5, the mapping will be different. Similarly, if I consider it 1, the mapping will be different. So it's kind of an interesting behavior that you can check. And for uniaxial direction, you can work on the material for calibration parameters. So you can also check for which material you want to consider this test to be calibrated here. So when you assign this material, it means the color of the material is changed here, and that material that we define here is used here. So this blue color in the beginning of this video series, if you remember, I discussed this, and after the discussion completion, I mentioned that if it is gray, it is not assigned to anything. If it is blue, it is assigned to something. So that's how we do it. And sometime at some stage we need some sort of initial stresses uh, in the model for which the randomized material wrapper is used. So that is the material wrapper in the material which can be defined here. So overall, we have covered this section. Then we are going to the acoustic medium for defining the acoustic media. Then we have this geotechnical elements and some other damage to the Pagels model, elastic isotropic, elastic orthotropic, and there are a lot of material models that I'm going to cover one by one based on the information available. And then we have concrete material and contact material. Then we have custom material definition, which is not important at this stage, and fluid side porous material, and all these materials we are going to use here. So after that, I will go to the uniaxial material definition, and for uniaxial material definition, the most used material that is present in the OpenSees and STKO in most of the studies as concrete and reinforcement steel, steel 02, steel 01, steel 03, and reinforcement steel, and Raymond Osgood steel and static model and or analysis. So and we have some elastic PP and other material definitions that are available in our analysis. So once the material section is covered, then we will switch to the sections, and after the section definition, we have some special purpose definitions for the models, and this thing will be covered completely. So this is getting very interesting, and it will be completed like this. After that, we have this element property definition. So for element property definition, we have these material definitions. We have discussed these absorbing boundary conditions, and there are a lot of parameters that are already discussed here. And for example, if we have zero length element, I discussed this previously as well in the previous lectures, but it can be covered here too. So this physical properties ND material up to uh, certain point of to randomized material, it is covered, and slowly and gradually we are trying to discuss all these materials before starting our practical projects. So thank you so much for watching, and I'll try to cover the other videos discussions in detail.